Welcome back. In this lecture video, we're going to look at the numerical measures of location and dispersion more closely and in greater detail. Now first off, let's introduce some notation. Let x1 through xn be a collection of n values. Then their sum is given by the usual expression that I'm pointing to here, x1 plus x2 plus and so forth, on out to plus x sub n. Now it takes a lot of writing and a lot of real estate on the page to express the sum in this way. And since we're going to be dealing a lot with sums in this course, we would like a more succinct, a more compact way of writing it. Now this sum is often abbreviated in this way that I'm pointing to here. In other words, the sum of the terms x1 plus x2 and so forth out to plus x sub n is represented in this compact way that I'm pointing to right here. Now, don't be thrown off by the notation. It's meant to make our lives easier in terms of writing these things down, expressing our ideas involving summation when we include these things in formulas and things like that. So to help you remember what this means, this notation here, this is the uppercase Greek sigma. And so if you think of the sigma, the S sound, that'll be a reminder that that is representing a sum. Now, there are several useful properties involving summation and the summation notation that we need to be aware of. So let's take a look at those. So here is the first summation property. Now, suppose that in the following expression that A is a constant that does not depend on I, so that it doesn't have I in the subscript. All right, and so what this says is that and we read this as the summation of whatever is over here. And so the summation of terms that look like a times x sub I is equal to, if we go to the end result here, a times the summation, a summation of terms involving only the x's. And so if we look at what this is saying, it looks like it's saying that we can factor that a outside of the summation. And that's in fact the case. And the reason we can do that is because, again, the a does not depend on the index of summation, which is I. So I is the index of summation. If we look at this notation here, what it's telling us is that we're going to sum up terms that are given by x sub I, where I goes from 1 to cap n. And since a does not depend on I, we can factor it out of the summation. And here's the mathematics that explains or that shows and justifies why we can do that. All right, if we write out the summation of a times x sub I, where I goes from 1 to cap n, if we write out what that means, then we have a times x1 plus a times x2 and so forth, dot, 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 out to plus a times x sub n. And so what we're doing there is expanding the definition of this summation notation. Now we see that we've got an a term. Each of these terms here involves a product, a times an x, one of the x's, and so we can factor the a out. And so we have, and going from here to here, we're just doing a very simple algebraic step, factoring the a out of the summation, and so we have a times the sum, x1 plus x2 and so forth, out to x sub n. Well, the term in the parentheses is just the summation of the x sub i's, I going from 1 to cap n. So if we think about this property, starting on the left-hand side here and going to the right-hand side, then we can think of this property as saying that the a factors out of the summation. And again, because the a does not depend on the index of summation, we can pull it out. We can pull it out front, we can factor it out. On the other hand, if we think about this property from the right-hand side going to the left-hand side, then what this tells us is that if we have a constant a multiplied against the summation being of the x sub i's, I going from 1 to cap n, then we can distribute the a across the terms in the sum. So we're just going backwards. And the justification would be just that. All right. And so how you decide to think about this summation property or describe it in words depends on the direction in which you think about this, but it's valid both ways, isn't it? So this is a very basic property. It's a very helpful property, and we use it all the time. So it's good for us to be familiar with this. Okay, property 2 looks like this. And if you'll remember back to your algebra days, whenever you have a sum of two terms, that sum is called a binomial. And so here we have a summation, I going from 1 to cap n, of a collection of binomials. And what this is saying, and again, if we skip past the justification here and go to the very last statement, what this is saying is that the summation of binomial terms is a binomial of the summations of the individual terms. Okay, so here on the right hand side we have a sum of two terms, so this is a binomial. It is a binomial. Each term in this binomial is a summation of the individual terms in the original binomial. So this is the summation of the x's, obviously. This would be the summation of the y's. All right, and so the summation of a collection of binomials is a binomial of the summations of the individual terms in the original binomials. So that's a very long-winded way to describe it, obviously. But if we wanted to put it in words, that's how we could do it. Now, the justification is very simple. All right. Again, we're just expanding out. In this first step, we're expanding out what this summation means. All right. So we have x1 plus y1 plus the binomial x2 plus y2 and so forth, out to plus the last binomial, x sub n plus y sub n. Well, we know by the commutative property of addition and the associative property of addition, utilizing two steps and going from here to this next statement, we know that we can regroup terms in the sum so that they look this way. All right, and so here we have the first summation in parentheses, x1 plus x2 plus plus x sub n plus y1 plus y2 plus out to x sub n. Well, in going from this step to the last step, we know we can express each of these as using the summation operators as shown here. So again, a very basic property, but again, very useful. And so we will be making use of that. Okay, here is another useful property, Summation Property 3. Notice here that we have a double summation. First, in the outer summation, let's call it the outer summation, the index of summation is I, and so I is going from 1 to cap n. And then in the inner summation, we need an index of summation there, and that needs to be different than the index of summation for the outer summation, so we'll call that j. And so in the inner summation, j is going from 1 to k. Now the terms in the summation are products, x sub I times y sub j. And what Summation Property 3 is telling us is that this double summation of terms that look like this, x sub I times y sub j, is equal to a product, the product, of the summations of the two variables themselves. So that double summation of the x sub I times y sub j terms would be equal to the product of the sum of the x sub i's, I going from 1 to cap n, times the summation of the y sub j's, j going from 1 to k. Now, in proving this, we are going to use one of the summation properties that we've already proved, Summation Property 1. So that's useful to be able to do, and that's why we introduced that summation property first. So to prove this, one way that we can do this, or one thing that we can do, is this is a double summation for each I. So we're going to set an I. We're going to start off with I being 1, and it eventually gets up to cap n. But for each of those i's, j is going to range from 1 to k. And so it's perfectly valid for me to put parentheses around this inner summation. Now, notice here that in this inner summation, the index of summation is j. All right, and so there's a j as a subscript on the y's, but there is no j on the x sub i's. X does have an index, okay, but it does, or a subscript, but it's not, that subscript is not equal to the index of summation on this particular summation. So from the standpoint of this summation here, x sub I is a constant. Okay, and so by summation property 1, we can pull the x sub I out of that summation, and so that is why we can do this. Now, we're now focusing on the outer summation, and its index of summation is I. And so from the standpoint of this outer summation, the terms that are being summed up are the products, x sub I, times this particular sum. Okay, now notice that this sum here, the sum of the y sub j is where j is going from 1 to k, that does not depend on I, which is the index of summation of this outer summation. And so again, by summation property 1, because that summation does not depend on I, we can pull that out front. Okay, we can pull it out of this outer summation. Well, and so here we have this summation, this double summation of these product terms is equal to the sum of the y's times the sum of the x's. All right, and we could stop there, but in order to get it in the same order, get the terms here in the product where the variables are in the same order as this, just to make it look a little nicer and perhaps easier to remember, we just use the commutative property of multiplication. So it's a very simple proof, and it does involve the first summation property that we came up with, and so that's very straightforward. And anyway, this is a very good, or a very nice and useful property as well. We won't use this one quite as much as the others, but it is useful to know, and so that's why we include it here. Next, we're going to look at various population and sample descriptive measures. So we'll start off by looking at population descriptive measures. So suppose that x1 through xn represents a population of n values. And so the key idea here, the key statement here is that this set of values, this collection of values, represents a population, not a sample. All right? It's very important that we distinguish between populations and samples in our thinking and as well as in our notation. Okay, so this collection of values represents a population of n values. The formulas and typical notation for the population mean, the population variance, and the population standard deviation are given below and on subsequent slides. So you'll remember back to the last lecture and the previous lecture that we were talking about measures of location and measures of variation. Measures of location tell us where a data set is located on the number line. It gives when we think of measures of location, we typically think of where the data set is centered in some way. And you'll remember that what we mean by center differs from one measure of location to another. So for example, the mean of a data set is, we can think of that as the center of mass of the data set. On the other hand, the median of a data set is a point that essentially divides a data set roughly in half. The mode of a data set would be the most prevalent data value if such a data value occurs. And so there are a variety of ways that we can represent the location of a data set. The variation or dispersion give us an idea of how spread out a data set is around its central values. So when we think about populations, numerical populations, we often want to describe those populations using these particular kinds of metrics, measures of location and measures of dispersion. And perhaps the most common way, the most common measure of location for a population of values is the population mean. Now, the notation that we'll use to denote a population mean, and again, I said it's very important that we distinguish between populations and samples, not only in terms of how our thinking about distinguishing between populations and samples, but also in our notation. And so we're going to have special notation that we use to denote a population mean. And that notation is the lowercase Greek letter mu, right? And so you think of the letter mu, and you think about when you say that, so that's that M sound, what we would call the M sound, they would call it the mu sound. But so that's why we use the lowercase Greek mu. for mean. And the definition for the population mean, when we have a finite population, the way that we define the population mean, and this shouldn't be surprising at all, it's just the arithmetic average of those n values. So we add up the n values. And again, notice that we're using this summation notation that we introduced in the previous lecture. So we have the sum, I going from 1 to cap n, which cap n being the number of values in that collection of values. And what are we summing up? Well, we're summing up the x sub i's. All right. And once we have that summation, then we divide that by the number of terms in the collection, which is cap n. Another way to think about that and to represent that notationally and mathematically is to multiply the sum by 1 over cap n. So that is the definition of the population mean for a finite population. If we have a continuous type of population where all values in an interval, for example, are contained within that population, then we would have to represent the population mean differently. We would have to express it using an integral, all right, and that involves calculus. And since calculus is not a prerequisite for this course, we're not going to really get into that notation, at least not right now. For our purposes right now, in terms of what we're talking about, it suffices to show this. This is sufficient for giving us an idea of what we mean by a population mean. Okay, the population variance is denoted by lowercase, this is the lowercase Greek letter sigma, and so the notation for a population variance is sigma squared. And that may seem strange that we would have sigma squared, that we would square that for some reason, but I'll explain that in just a second. The defining formula for the population variance, again for a population that is finite, it is given by this expression. And we can think of it, well, let me just read off the formula here. It's the summation. So again, we're utilizing this summation notation. Then what are we summing up? Well, we're summing up squared terms. And each term that is squared is the difference between x sub I, the ith x value, and the population mean. And so each one of these quantities inside the parentheses represents a deviation between each x sub I and the overall population mean. And then we square those deviations, and that squaring makes all of these values non-negative, either 0 or positive. So we're adding up, we're summing up squared deviations of each observation from the mean. And then once we've added all those squared deviations up, we divide by cap n. And so this is, we can think of this, if we think about what this means and describe it in words, it's an averaging process, isn't it? Because we're adding things up and then dividing by the number of terms in that sum. So this is the average squared deviation from each observation and the mean. And this is the defining formula, the definition formula for the population variance. Now, note that we can take this defining formula for the population variance and do a little bit of algebra, and I'm not going to show the details here. I'll let you work that out. But what it involves basically is squaring these binomials, all right, and then utilizing properties of the summation, okay, in the resulting quantity once you square that, and simplifying, and you get an equivalent expression given here. So this expression right here is algebraically equivalent to the defining formula. And it's typically quicker to calculate a population variance using this formula than it is to use the defining formula, because you don't have to calculate the individual differences before squaring. Notice that all you have to do here is square each of your x values, and then add those squared x values up and then divide by n. So this first term is an average squared, is the average of the squared x values. And then once you have that, then you do only one subtraction. Here you've got to calculate n differences. Here you've only got to calculate one difference, all right? And you subtract off the squared value of the mean. And so because this is typically quicker to use, we might call it a computational formula. We could also call it an expansion formula, because we are expanding this squared binomial into its constituent parts, and then applying the summation to those parts and simplifying to get this. But the important thing to realize is that this is algebraically equivalent to the defining formula. You can use either formula. In some cases, there are some examples where the definition formula will be more efficient to use or easier to use, but in perhaps most cases, this computational formula will be quicker to use. Okay, so those were the population measures. Now let's look at sample measures. Now, let's talk about the, actually I need to correct myself here. We're not going to talk about the sample measures yet. And I see that I have, because we're still talking about the population variance, but I do have in the titling here the word sample. Well, that's a typo. So I'm going to magically fix that while we're creating this video. All right, so here I've got the corrected title for this slide. And so in your course note packet, you go ahead and make that change as well. So this is continuing on from the previous slides. And so the population variance can therefore be calculated using either of the following formulas: the definition formula or the computational formula. Which one you use in a given context will depend on really which one is easier to use and perhaps what information you have. If, for example, you've been given the sum of the x's and the sum of the squared x's, then it is probably going to be more useful for you to utilize the computational formula. And even if you've got all the data in front of you, it may be more time consuming to calculate the population variance using the definition formula, because again, you've got to calculate n differences before you, and then square those differences. Here, you only have to calculate one difference. But again, it depends on the situation, so you just need to look at that situation and see which is going to be most convenient for you. Another measure of dispersion of a population is the population standard deviation. Remember, in our previous discussions about measures of dispersion, when we talked about the variance, we said that the units, we pointed out that the units of the variance are the square of the units of the data, and that may be difficult to interpret or explain. And so one way to alleviate that problem is to calculate the square root of the variance. In doing that, we would calculate the square root of the units. And so if we calculate the square root of the squared units, then we get back to the units of the data. And so that's one of the reasons that we calculate the square root of the variance. And in doing that, we get the population standard deviation. So remember, in general, the standard deviation is the square root, the positive square root of the variance. And so when we're talking about populations, the population standard deviation is the positive square root of the population variance. We're going to denote the population standard deviation by lowercase sigma, all right, for that S sound, that S sound, the sigma sound, reminds us that we're talking about the standard deviation. And this is why we use sigma for the population standard deviation. And then because the variance is the square of the standard deviation, that is why, let me go back a slide or two, that is why when we define the notation for the population variance, that's why we call that sigma squared, because if we think about it this way, the variance is the square of the population standard deviation. So that's the source or the origin of this notation. Okay, so how do we calculate the population standard deviation? Well, again, it is the square root of the population variance. So I've just got the population variance represented a couple different ways here. It really suffices to just utilize or to show this right here, because again, there are two ways to calculate the population variance. But the population variance is denoted using this notation. Anyway, that is how we calculate the population standard deviation. So these three quantities that give us information about the population mean, the population variance and the population standard deviation. The population mean being a measure of location, the population variance and the population standard deviation being ways of describing how spread out or disperse the population is. Next, we look at these descriptive measures for samples. And so suppose that x1 through xn represent a sample of n values. Now, before I go on, I just want to point out that in what we're talking about now, notice that the x's are lowercase. In talking about descriptive measures for populations, we used uppercase x's. And so that is a distinction that I will use throughout the course in the notation. Typically, when we have an observed sample from a population, then we would denote those observed values by lowercase x's. If we're talking about random variables, all right, so we're representing what we could select from a population, but we have not actually observed those values yet, then we would use uppercase x's. So that's a distinction that I'll adhere to. And also notice that the size of the sample is denoted by lowercase n as opposed to capital N. So when we talk about populations, a finite population with n values, then we would use the population size or denote the population size by uppercase n, as we did, as you saw in the previous lecture. But when we're talking about samples and the sample size, we're typically going to represent that using a lowercase n. All right, now the formulas in typical notation for the sample mean, the sample variance, and the sample standard deviation are given below and on the following slides. So we'll start off by talking about the sample mean, and this is commonly denoted by the letter used to represent the observations or the data, and then we put a bar over the top. So since we're denoting the data values, the observations, using lowercase x's, then to denote the sample mean of those values, we would use that same letter, lowercase x, and then we would put a bar over the top. And so then we describe this or say it verbally as x bar. So the sample mean, x bar, is just, as you would expect, the arithmetic average of the values in the sample. The sample variance, which if we think in general about what a variance represents, it represents the average squared deviation about the mean. In this case, it's the average squared deviation about the sample mean, and so this is how we would calculate the sample variance. This is the defining formula. And so first, note that we are summing up the squared deviations from each of the sample values, each of the x sub i's, from the sample mean, x bar. All right, and once we've calculated those deviations, we square the deviations, and then we add up those squared deviations. Then, again, the sample variance is it's an average squared deviation about the mean, and so we need to average. We're averaging these squared deviations, so once we add them up, we're going to divide by something. Now, you may think that we would divide by lowercase n, which is the number of values, it's the number of squared deviations that we're averaging. But for reasons that we will not go into at this point, I will in a later lecture. Instead of dividing by n, we divide by n minus 1. Now, again, that may seem strange or counterintuitive. There is a reason, there's a good reason for doing that. And we'll talk about that when we get into the section on sampling distributions. Now, how do we denote the variance of a sample? Well, we're not going to use sigma squared, okay, because sigma is reserved for a population. So the way that we would typically represent a sample variance is using the letter s and then squaring it, so s squared. And I can also subscript s squared with the letter that we're using to describe or denote the observations, in this case x. We don't always have to have a subscript. We can use it or not, but if you've got more than one variable that you've collected and have in the sample. So maybe you've got an x values and you've got y values in the same sample. Then we may want to differentiate the variance of the x's from the variance of the y's in our notation. So we could have s squared sub x, s squared sub y. In the same way that we have a computational formula or a shortcut formula for the population variance, we also have shortcut or computational formulas for the sample variance. And it turns out that we've actually got a couple different ways, shortcut methods for calculating the sample variance. Again, here we have the defining formula, all right, that we just looked at. But after we expand the square, so expand that term right there, and then utilize summation properties, go through a little bit of algebra, we have the following two computational formulas. All right, and so which one of these formulas you use will depend on which is going to be easier to compute, which is going to be quicker to compute, and it may also depend and will depend on the information that you actually have. So you may have some summary statistics about a sample. You may have, for example, the sum of the x's and the sum of the squared x's. And if that's all you've got, then it may be easier to use this third expression here, rather than the defining formula or the first computational formula. On the other hand, if you have the sample mean and the sum of the squared x's, then it may be easier and more straightforward to use this second formula here. You get to choose which one of these you use. Just make sure that when you are using these computational formulas, and in particular this second one here that involves the sample mean, where we square that, make sure that you use as much precision as possible and in particular the sample mean, because once you start rounding these quantities, then you start introducing rounding error into the calculations. And so, for example, if the sample mean has been rounded to a small number of significant digits, or perhaps if we think about it in terms of a small number of decimal places, then if we utilize this formula, we may get a slightly different value than if we were to use the definition formula or the computational formula because of that rounding. So you just be careful. Whenever you're calculating a sample variance, for example, and really any quantity where you've got other quantities that you've calculated beforehand, make sure that you carry as much precision in those intermediate calculations, as much precision as possible, so that you minimize the amount of rounding error that you have in the sample variance. But keep in mind that these three expressions are algebraically equivalent, so apart from any rounding errors, you will get the same value. All right, so this slide just summarizes those results so that we have all three formulas on one slide. I will just tell you that my preferred shortcut formula or computational formula to use is computational formula 2. I tend to use this one because there is typically less rounding error in the second computational formula than there is in the first one. Let's introduce and talk about some terminology as well as some additional notation. So this quantity that has shown up, the sum of the squared x values. This is, again, it's called the sum of the squared x values, but it's more succinctly described as the sum of squares. Okay, and so we also have, in the defining formula for the sample variance, we have this expression here. Before we described this as the sum of the squared deviations from each of the observations and the sample mean. Now, this is also described or called the sum of squared x values corrected for the mean, or more succinctly, just the corrected sum of squares. Now, this term correction for the mean means that the data are centered before they're squared. By centering, we mean that we subtract the mean from each observation before squaring. It doesn't mean that we've made a mistake. We're not correcting a mistake. What this means is that, again, we've subtracted off the sample mean. Another way that we could describe this, instead of using the word correction, we could use the word adjusted. So we could perhaps call this the sum of squared x values adjusted for the mean, or more succinctly, the adjusted sum of squares. And I think personally that would make more sense and be less confusing, but this term correction or corrected sum of squares and the sum of squared x values corrected for the mean, this is been around, it's terminology that's been around a long time, right? And so we need to be aware of that, and we'll use that when we need to. Now, there's additional notation that we can use to represent this corrected sum of squares. And this notation is S sub xx. Okay, so the subscripts here, x, correspond to the label I'm using to denote the data values. So if I were to use y's to represent the data values, then this would be S sub yy and so forth. But we're using x here, and so the corrected sum of squares for the x's would be S sub xx. And again, it's just defined to be this summation here. So we've seen this summation. It's the numerator of the sample variance. And that numerator, instead of having to write out this summation, again, for efficiency purposes and to reduce the amount of writing, we're introducing additional notation, additional abbreviations for some of these quantities. So S sub xx, okay, it's a very important quantity for us to know about and know what that notation means. And it just means the corrected sum of squares. Once we have the sample variance, then we can calculate the positive square root of the sample variance to get the sample standard deviation. And as you would guess, because we are taking the square root of s squared, then we're going to denote that square root by s. And so s, capital S, is the typical notation for the sample standard deviation. So if we're calculating things by hand, for example, from the values, let me scoot back here to a previous slide. So if we're calculating these measures of dispersion for a sample using these summary statistics, like the sum of the x's and the sum of the squared x's, and we know this to be the sum of squares, or if we're calculating it using the definition formula, then we would calculate the variance first, and then from that calculate the standard deviation. So that's the order that we would calculate these two measures of dispersion if we were calculating it from the raw data by hand. Now, let's suppose that we have a bivariate sample of data points. And so each observation corresponds to an ordered pair rather than just a scalar. And so the first observation would be x1, y1. The second observation would be x2, comma, y2, and so forth, up to the nth observation in our sample, x sub n, comma, y sub n. So we have a bivariate data set. Now the corrected sum of products, okay, the corrected sum of products of x and y, which is denoted by s sub xy. And this is analogous to what we did back here for the corrected sum of squares of the x's. But now the summation involves two variables, x and y, and so that's why we have x and y in the subscript. So the corrected sum of products of x and y, which is denoted by s sub xy, is defined to be this summation here. And again, I'll just point out, notice that we're using this summation operator all over the place. So it's defined to be a sum of n terms. Each of the n terms is a product of the deviation between the two variables and the means of the respective variables. So x sub I minus x bar times the quantity y sub I minus y bar. So that's what the terms in this summation are, and we add those up, and then once we do that, that gives us the corrected sum of products of x and y, or s sub xy. Now, if you use the FOIL method, all right, and expand out that product, then and then apply the summation operation to those terms, and use a little bit of algebra and simplify, then what you get, are two computational formulas, all right, that are algebraically equivalent to the defining formula. And again, which one you use will depend on what information you have. So for example, if you're given the sum of the x's times the y's, as well as the mean of x and the mean of y, then you could use this formula very easily. On the other hand, if what you're given is the sum of the x's, the sum of the y's, and the sum of the x's times the y's, then it would be perhaps more straightforward just to use this last formula. So depending upon what information you have, again, you'll just pick the formula that would use to calculate this corrected sum of products. Now, once we have the corrected sum of products, S sub xy, we can calculate the sample covariance. The sample covariance really is just an average corrected sum of products. What we can think of is once we've added up, okay, these products, then if we divide by the appropriate value, we can think of this as an average sum of products, sum of corrected products. Again, so instead of dividing by n, and this is the reason for dividing by n minus 1 here is going to be the same as dividing by n minus 1 for the sample variance. We won't really get into that right now. Anyway, so this is how we would calculate the sample covariance. So again, corresponding to, let me go back one slide, corresponding to each of these representations for the corrected sum of products, we have a corresponding formula for the sample covariance. Now, the sample covariance, what does this give us? We know that the sample mean is a measure of location. We know that both the sample variance and the sample standard deviation are measures of variation or measure of dispersion, how spread out a data set is. What is the sample covariance measuring? What information is it giving us? Well, when we have a bivariate data set, it's going to be interesting and helpful for us to know how the two variables vary together. And the sample covariance is a step in that direction. The sample covariance is a measure of how x and y vary together in that particular sample. So this is one way of calculating or determining, quantifying the extent to which the two variables x and y vary together. One thing to think about, what are the units of the sample covariance? And so if we think about, notice that there are no units associated with the denominator here. And if we go back to the previous slide, right, where we're looking at what we know to be the numerator of the sample covariance, then the units on the difference of x sub I and its difference, and its mean, x sub I minus x bar, the units of that difference are going to be the units that are attached to the x's. And the units associated with y sub I minus y bar are the units of the y variable. And so the units of the corrected sum of products is the product of the units of the x's and the units of the y's. Okay? And so the sample covariance has units that are the same, the product of the units of the x's and the units of the y's. And so this measure of how x and y vary together that is provided by the sample variance depends on the units of the x's and the y's, doesn't it? Numerically, the numerical value of the sample covariance depends on the units that are used to measure the x's and the y's. Now, a measure that does not depend on the units is given by the sample correlation. The sample correlation is denoted using the lowercase letter r, all right? And because we're talking about the sample correlation between x and y, we could, and very often we will, list those two variables as a subscript to the sample correlation r. Now, the sample correlation is defined to be the sample covariance divided by the square root of the product of the sample variances. So if you look in the numerator here, okay, this is just the sample covariance. This is what's on the previous slide. All right? And so we have the sample covariance divided by the square root of the product of the sample variances. And you can rewrite this in a variety of ways. All right, I'll let you look through these and verify in your own mind that these other representations are equivalent to the defining formula. But the one thing I would point out is that in the sample correlation, the units of the numerator would be the product of the units of the variable. So the product of the units of x and the units of y. Well, the denominator has the same units, and I'll let you convince yourself that that is true. Just remember what the units of the sample variances would be, and then that you're taking the square root of those units. So the sample correlation gives us another measure of how x and y vary together, as the sample covariance did, but it has the advantage of not depending on the units of the data. Right? And so you can, with the sample correlation, you can change the units of either your x's or your y's, or both, and it's not going to affect numerically the value of this sample correlation. Now, it can be shown that the sample correlation is measuring a very specific type of relationship. In particular, the sample correlation is measuring the strength of the linear relationship between the two variables x and y in a particular sample. So it's not measuring the strength of the quadratic relationship or some other kind of relationship. It's specifically measuring the strength of the linear relationship between the two variables in the sample. All right, now let's talk about how to calculate these summary measures using your calculator. Now, to use a hand calculator to compute descriptive measures, you must first enter the data into the calculator's statistical memory and then request the desired descriptive measure by pressing the appropriate button or menu option on the calculator. Now, there are usually buttons for the mean and the standard deviation of a data set. The variance is usually not provided but can be obtained by squaring the standard deviation. So whereas if we were calculating the measures of dispersion by hand, we would calculate the variance first and then from that calculate the standard deviation, when we are using the statistical functionality of the calculator will give us the sample standard deviation, or I'm sorry, the standard deviation. And if we want the variance, then we would have to explicitly square that standard deviation that we obtained. Often, we're not really going to need the variance. What we're really after, in many cases, is the standard deviation itself. And so that is why calculator manufacturers and designers give us the sample standard deviation itself rather than the sample variance. Now, the button that instructs the calculator to compute the mean is typically labeled X bar. And you'll remember the calculation, the formula for calculating the mean of a population is the same as the formula for calculating the mean of a sample. The only difference being in how we denote it. For a population mean, we would use mu to represent that value. And if we're dealing with a sample, if we consider the data set to be a sample, then we would denote the mean of the sample mean of the x's by X bar. So the calculator only needs to give us a single button for calculating a mean. You know, whether it's a population or a sample, we just need to keep that in mind because typically we would consider a data set to be a sample. The calculator manufacturers have chosen to represent that button using an X bar rather than a mean. Now, obtaining the standard deviation from the calculator can be a little confusing since there are usually two buttons that provide a standard deviation. There are two buttons, and so the button that you will use to calculate a standard deviation will depend on whether the data set is considered to be a population or a sample. Now, the button labeled sigma returns a value given here, which you'll recognize as being the standard deviation of a population. And so if you use this button or this menu option to obtain a standard deviation, keep in mind that you are considering the data set to be a population. Now, that may or may not be what you want to do, so you need to be very careful. Now, there's going to be another button or another menu option that would consider the data set to be a sample and calculate the appropriate value based on that. In some calculators, for example, the TI-84, the 83 and 84, that menu option is going to be an S, which is consistent with our notation. On some other calculators, and perhaps older calculators, the button itself will be denoted by sigma again, but with an n-1 as shown here. And so what that means is that it's performing this calculation to get the standard deviation, and because that is dividing by n-1, we know that that is then treating that data set to be a sample of values. So you just need to be aware that there are two buttons or two menu options on calculators that have this kind of statistical functionality, and they're calculating the standard deviation either dividing by n, which is what you would do if you consider that data set to be a population, or dividing by n-1 if you consider that data set to be a sample. So you just need to be very careful in the value that you obtain from the calculator. Now in this lecture we're going to look at descriptive measures for a linearly transformed data set. So again, when we talk about descriptive measures, we're talking about things like the mean of a linearly transformed data set, the variance and standard deviation of a linearly transformed data set. Now, let's start off by letting x1 through x sub n represent a sample of n values. For each I going from 1 to n, let's define a new variable, a new measurement, a derived measurement, which we'll denote by y in this case, in terms of the x's in the following way. So y sub I is equal to a times x sub I plus b. A is going to be non-zero, all right, to be of any interest. B could be 0. Really, B can be any real number. A can be any real number except 0 in this case. So specifically, y1 would be a times x1 plus b. y2 would be a times x2 plus b, and so forth out to y sub n being a times x sub n plus b. And so the question is, how are the mean, the variance, and the standard deviation of the y's, the new variable, related to the mean, variance, and standard deviation of the x's? Now, the thing I would point out, and it's denoted here in the title of the slide, is that this is a linear transformation of the x's. The y values are a linear transformation of the x's. The slope would be a, and the y-intercept of that transformation would be b. So this is indeed a linear transformation of the x's to the y's. And so, again, the question is, how do the mean, variance, and standard deviation of the y variable relate to those of the x variable? And it turns out that there's a very nice and intuitive relationship, very easy to prove. The relationship between the means of the y's and the x's. Well, if x bar is the mean of the x's, then the mean of the y's is going to be a times x bar plus b. So the mean of the y's is the same linear transformation of the x's, but it's the linear transformation applied to the sample mean of the x's. How is the variance of the y values related to the variance of the x values? Well, it turns out that the variance of the y values is equal to a squared times the variance of the x values. All right, so what is a? Well, that's the slope, all right, of this relationship. It's the value that we're multiplying against the x's. And so this is how we could very easily, if we knew the variance of the x's, and we were considering this linear transformation from the x's to the y's, then we could very quickly calculate the variance of the y's using this formula. And then how is the standard deviation of the y's related to the standard deviation of the x's? Well, we can very easily obtain that by taking the square root of both sides of the equation in the previous bullet point. And so the standard deviation of y's is equal to, and actually what I need to make this completely 100% correct is have absolute values around the a right there, because again, this a up here could be negative, but that would certainly not be negative there. All right, and so here I've magically corrected that. So make sure that in your course note packet on this particular slide, you correct that and put the absolute value bars around the A. Okay, now where do these relationships come from? How can we derive these relationships? Well, it's very easy. All right, so we want the sum of the y's as shown here, and I'm sorry, not the sum of the y's. We want y bar, and remember y is related to x according to this linear relationship on the previous slide. And so by definition, y bar is equal to 1 over n times the sum of the y values. And if I replace each y sub I by its representation in terms of the x's, we have 1 over n times the sum of the binomials here, a times x sub I plus b. And now we can invoke properties of summation that we started off in this section talking about. And I'm combining a couple steps here into one step, but by using properties 1 and 2 of summations, then we can re-express this expression here in this way: a times 1 over n times the sum of the x's plus 1 over n times the sum of the b's. Well, this quantity right here is just x bar, and note that this quantity here, we're just adding b up n times, so that's n times b, but then we divide that by n, so the n's cancel out, and so we have y bar being equal to a times x bar plus b. To derive the relationship between the variances, I'm going to write out first what the definition of is for the variance of the y's. And then what I will do is I will replace each y sub I by what it's equal to in terms of the x's, so a times x sub I plus b. I'll subtract off y bar. Now, in the previous slide, in the previous result, we showed that y bar is equal to a times x bar plus b. All right, so I'm using the result that we just obtained. And then I'm going to rearrange things in here using commutativity and associativity of addition and all that kinds of stuff. And anyway, this simplifies. Notice that the b's cancel out. We've got a plus b and a minus b in here. And so I've distributed the negative sign across these two terms. And I've rearranged the values in the sum. And so notice here that the b's go away. And then I can factor the a out. All right, that's property 1. And then I get this expression here, which is just the variance of the x's. All right, and so the variance of the y's is equal to a squared times the variance of the x's. And then to get the standard deviation of the y's, we would just take the square root, the positive square root of the variance of the y's. So this is what we would get: the absolute value of a times the standard deviation of the x's. Now, I had to make the same correction on this page that I made a few slides ago. So make sure in your notes that you put the absolute value around the a. All right, now let's look at descriptive measures for a particular kind of linearly transformed data. So again, we were just looking at descriptive measures for linearly transformed data. And one special case of a linear transformation is when we center and rescale a variable. And so let's look at this. So let x1 through xn represent a sample of n values. For each I, ranging from 1 to n, let's define a new random variable, or a new variable, that we'll call z, and in particular z sub I going from 1 to n, in terms of x sub I, by doing the following computation. For each I, going from 1 to n, we'll let z sub I be equal to the following expression. We're going to subtract off the mean of the x's from each x sub I, and then we will divide that entire difference by the standard deviation of the x's. Now that process is called standardization. Right? We are centering the data by subtracting off the mean of the x's from each x sub I, and then we're rescaling the data by dividing the differences by the standard deviation. So the question is, what are the mean, variance, and standard deviation of the z's? Now note that we can write z sub I as a times x sub I plus b, All right, so in other words, we can write this new variable as a linear transformation of the x's in this way, where a is equal to 1 over s sub x, and then b is equal to negative x bar over s sub x. And so from the results that we obtained on the previous slides, right? So from this slide here, applying these results to this particular situation, we can very quickly conclude that the mean of the z's, the sample mean of the z variable, is now 0. Okay, and this is why we call this centered data, right? Because now it's centered at 0. The variance of the z's is 1, and so therefore the standard deviation of the z's is also 1. And again, where do we get these results? Well, this is the z sub I, the formula for computing z sub I from the x's is a linear transformation, where a is equal to 1 over the standard deviation of the x's, and b is equal to negative x bar over s sub x, the standard deviation of the x's. And we're applying these results here on slide 24 to that situation. All right, so this is very important for us to know, and we do this all the time in applied statistics, this process of standardizing the data, where we recenter the data and rescale the data. We center the data at 0, and we rescale the data so that it has a standard deviation of 1. Now, this transformed variable, z sub I, this centered and rescaled variable, z sub I, is called the z-score of the x's, and it tells us how many standard deviations a particular xi is from the mean x bar. So again, the units on z sub I, we can think of it as there being no units, or we can think of it as being units of standard deviations of the x's. All right, so this centered and rescaled variable is called the z-score of the x's, and what it tells us is how far is x sub I from x bar in terms of the number of standard deviations of x. And that type of distance, the number of standard deviations an observation is from its mean, the mean of that data set, is going to be a very important quantity that we're going to make use of in statistics and in this course in the context of hypothesis testing and things like that. So it's a very important quantity for us to know and understand and to know how to calculate.